Welcome back once more to another exciting episode of Dave Does Math from Home. This video is going to be very short. We're just going to wrap up some of the stuff we did in section 3.3. This is part 3 of that series. So let's get right into where we left off. We left off with a couple big ideas. Things that are safe are addition, subtraction, and coefficients. These things behave exactly like you think they ought to behave when you're taking derivatives. If you're taking the derivative of a bunch of terms that are all added or subtracted and they're just like x to some power with a bunch of coefficients, then you're all set. More on that in a minute. Things that are unsafe are multiplication and division and composition. If you take two functions and multiply them together and then try to take a derivative, the derivative of that product is not the product of the derivatives. The derivative of a quotient is not the quotient of derivatives. The derivative of a composition is not the composition of derivatives. These things are not safe. They do not behave in a way that you would think is sort of like very simple and intuitive. They can be done, and we're going to do them very soon. It's just not as simple as you would like to think. So you have to approach them with caution. That's really all I mean when I say that they're unsafe. And we have the power rule, which says that if we're taking a derivative of x to the n, it should be nx to the n minus 1. We no longer have to use limits of difference quotients to find derivatives of things that look like this. And the really, really good news about the power rule and these things is this lets us take the derivative of anything that looks like some coefficient with some x to some variable plus a different coefficient and an x to a different variable minus another coefficient and an x to another variable. Any amount of coefficients can be anything, x's to powers that are being added and subtracted together, we can always find the derivative of these things very easily, which is good because that description includes all polynomials. At the very start of this class I mentioned that polynomials are nice, they're well behaved, they're always smooth, continuous, differentiable. This is part of what I mean by well behaved. Finding the derivative of a polynomial is always very easy because we have the power rule and we know that addition and subtraction and coefficients are safe, and addition, subtraction, coefficients, and powers are literally every possible polynomial that you could ever have. So if we wanted to take a derivative of this, let me do it down here actually. To take a derivative of this, you can bring derivative of x to the fifth is 5x to the fourth. Coefficient is safe, so that stays there. 3 times 5 will be 15. Derivative of x to the fourth is 4x cubed times 12 should give us 48x cubed. Derivative of x squared is 2x times negative 7 should be negative 14x. This is it. If you take the derivative of a polynomial, you should always get a polynomial. You should always have one less degree than the polynomial you started with. Derivatives are all very nice and well behaved. The other thing I want to talk about before we wrap up section 3.3 is, for now, what to do about stuff that looks like this, or even this. Right now, eventually we will end up with rules that will allow us to do derivatives of these things. This one we're going to handle with something called the product rule. This will handle with something called the quotient rule. This will handle something called the chain rule, which is probably the most important thing we're going to do in calculus. Because once we understand the chain rule, we can kind of go back and have a better understanding of what all of this means. But for now, we don't know these things, and the homework is going to try and trick us. The homework is going to give us problems that look like this. 5x squared minus 3 times x to the 4th plus 2x. The homework is going to ask you for the derivative of something that looks like this. And sort of it's a trick. They're trying to trick you. They're trying to get you to take the derivative of this and take the derivative of this and then multiply them. You can't do that because multiplication is not safe. This is a product between two things. The derivative of this is not the product of these two derivatives. We can't do it like that. There is a way we can do this as a product, but we don't know that yet. So when we find problems that look like this, what you have to do is just simplify. We know how to FOIL. We can turn this into one big polynomial expression. And once it's in one big polynomial expression, it just involves a bunch of addition and subtraction, which are safe, and not multiplication, which is not safe, then we can take the derivative that way. So for this problem, it's going to look like 5x to the 6 plus 10x cubed minus 3x to the 4th minus 6x. I think this is what I get when I FOIL this out and simplify it. And now we just have a polynomial. We can take a derivative very easily. 30x to the 5th, 30x squared minus 12x cubed minus 6. That's it. That's your derivative. Quick side note before I close this out. Linear things always just turn into their slope when you take a derivative. If you take a derivative of a constant, if you're taking a derivative of something like 5x plus 2, the derivative of this is 5. Derivative of this, you can consider this an x to the 0 term, and this an x to the 1 term, which is why this turns into 5x to the 0, which is just 5. And this is going to turn into 0, and you do nothing with this. So constants, the derivative of a constant is always 0. I lied about this being the last thing. There's one other thing. E to the x is considered another sort of basic-ish derivative. The derivative of e to the x is, brace yourselves, e to the x. Mentioned in pre-calculus that e is sort of like the quintessential base for exponential functions. It's like it has a fundamental importance to exponentials in the way that pi has a fundamental importance to circles. This is the big reason for e's fundamental importance. No other exponential function does this. Other exponential functions, if you try to take a derivative, it'll be close to what you started with, but not quite exactly the same. E is the unique singular number that if you use it as a base of an exponential function, the derivative is exactly what you started with. E to the x turns into e to the x when you take a derivative. I'm not going to prove this with a limit, but I can talk about it briefly with graph. If you start with something like e to the x, if you want to sketch a graph of the derivative of this, you need a function back here. It's very flat, so it's going to be 0-ish. Over here, it's starting to increase and get more and more positive. The slopes here are very, very, very positive. The slopes here are more positive. The slope here is positive-ish. So if you're trying to sketch a derivative function, it needs to be 0-ish back here, small numbers, medium numbers, and big numbers up here, which is exactly what this shape already is. small numbers, medium numbers, bigger numbers, really big numbers. This shape is unique in mathematics in that the slopes of all of these tangent lines end up falling right on the value of the function itself. So that's very interesting. This is actually the last thing I meant to say about section 3.3. So stay tuned for some new videos about section 3.4. We're gonna do this stuff.